Okay, thank you for joining us for this session. So our session is about the high quality data for the cold region operations. So I work with Professor JC and also another Angel, but we invite Marta to join me to chair this session. And we have 6 talks and another really light panel, and have several questions. We would like to discuss the future of the geocode region and also for the cryosphere service for the next generation of the AI Earth observation intelligence. So I'm the first phase chair on that. So please help to. The first talk is from UNESCO, Dr. Yang Wei. Yes, please.
At UNESCO. It's my great honor to briefly introduce the implementation of the Decade of Action for Cryosphere Science. Glacier mass loss have accelerated worldwide and has lost more than 6,500 gigatons of ice during the past 2 decades, contributed to more than 18 millimeter rise in global sea level. This change affects over 750 million people, including residents of small island developing state. For reference, there are 35,000 glaciers distributed across the UNESCO World Heritage worldwide, covering an area of 100,000 square kilometers. They account for 15% of the planet's total glaciarized area. Even if global warming is stopped now, 1/3 of this glacier will gone under current temperature growth trend. The cryosphere refers to all frozen water on Earth, including polar ice sheet, the ice permafrost, snow covers, and so on. The climate crisis is causing several damage to the cryosphere. Cryosphere melting is close to linked with the sea level rise, fresh water resource, and the geological hazard. It may also trigger the potential climate collapse by weakening the Atlantic meteorological overturning circulations. So in 2022, UN member states adopted a resolution on the International Year of Glacier Preservation 2025. French President hosted One Planet Polar Summit in 2023. The summit put forward the proposal of the International Decade of Action for Cryosphere Science, which was approved by the United Nations General Assembly in 2024. The UN General Assembly resolution highlights 3 core dimensions. It's called in-depth understanding of cryosphere and hydrological system, ecosystem change and their impact on social, economic, vulnerability, and adoption. It also advocates sharing the best practice to building resilient society. So it invites UNESCO to lead the decade. Following the World Glacier Day 2025, UNESCO held a brainstorming session in Paris in March 2025, gathering scientists and policymakers. The decade was officially launched in last year by French and Tajikistan president. UNESCO invites numerous scientists to compare 5 backing ground documents guiding the discussion. This document covers scientific observation and modeling, policy advocacy, socio-economic impact and adoption, education and capability building, and financial gaps assessment. So this document was revised and compared into a synthesis report. We have identified 5 overarching challenges for the cryosphere decade, including the global cryosphere monitoring, cryosphere projection, cryosphere risk management, cryosphere adaptation, and amplifying the influence of cryosphere science. 3 core goals are set under each overarching challenge. Take the first overarching challenge as a global cryosphere monitoring as example. Its goals are to build a global cryosphere monitoring inventory, improve the monitoring capability, and turn operation data into practical guidance. Indeed, global cryosphere monitoring encountered huge difficulties. Harsh natural conditions and data gaps hinder ground-based operation, especially in high mountains and Antarctic. Satellite operation also face physical constraints and uncertainties. Besides, the traditional monitor focused merely on physical change, ignore far-reaching social impact on indigenous communities. To check this difficulty, the first overarching challenge is set 3 milestones. Firstly, establish a comprehensive operation database to identify geography, variable, and methodological gaps, and formulate unified data policy for the decade. Secondly, improve the cryosphere monitoring capability by applying new technology, including satellite, AI, and the local community knowledge. Third, connect the operation data with the prediction model and the decision-making procedure to generate a practical solution. So this geoside event put forward 3 objectives. These 3 objectives are highly consistent with the 3 milestones of global cryosphere monitoring. To implement the cryosphere decade, UNESCO established a governance structure mechanism. The governance structure has 3 levels, including management, strategy, implementation. At the implementation level, corresponding to the above-mentioned 5 overarching challenges, 5 working groups will play as the basis implementing partners. So the official website now open call for interesting registration for all working groups. We have received over 350 applicants for the 5 working groups, Financial Dialogue and the Cryosphere Alliance. So each group is structured with 1 leader, 2 associate leader, and 1 secretary. Co-members will be confirmed by group leaders. Our working group opened in an open model, welcome all willing contributors. So the decade is divided into 3 3-year phases. Each phase will conclude with our triennial summit to display the group achievements. The first triennial summit is proposed to be held in Beijing, China. So we will carry out joint implementation with the International Polar Year, International Ocean Science Decade, and the Sustainable Development Science Decade, so as to realize a synergy among global cryosphere-related activities. There are all partners united under the UNESCO. We welcome your partner to join this cooperation network. This is a very brief introduction to the cryosphere decade implementation. We sincerely welcome everyone to participate in relevant activity and project of the cryosphere decade. Thank you very much.
This one, yeah.
Good afternoon. My talk is on the snow study and data products over Tibet Plateau. My name is Jianqing Shi. Go next. So basically over Tibet Plateau, the snow has very different characteristics. It's typically over the central part of Tibet Plateau. The snow comes and goes very quickly, and most of the snow is over the mountain. And we basically evaluated the current reanalysis data and satellite products, and it's typically showing its the reliability is quite has some challenges. So the project mainly carry out for the science question is first is a spatial and temporal distribution of seasonal snow over the different scales. And secondly, how does that change it over the last 20 years? And the third one is how much water is actually supported to the Tibet Plateau. Next. So for the snow-covered area, basically, if we always fighting between the spatial and the temporal. So we're using the medium resolution, but can carry out the higher spatial resolution. And over the Tibet Plateau is actually, as I mentioned, it's in the central part. The snow comes and goes very quickly. So we need a daily product so that we have to estimate is snow-covered fraction. And the bottom figure, it shows the two MODIS satellite, it still covers 40% cloud cover. And if we use geostation satellite, then it can get to the less than 10% of the cloud cover. And so that for the validation, we have more than 2,000 Landsat data used for validate fractions snow cover. That means we estimate percentage of snow cover at each pixel. And it shows our basically the error is standard error is less than 13%. So this is our products. And for the snow depths, we also compared with with satellite measurements from the EMSA2 and also from the global snow, and it also shows some uncertainties. So what we have developed is two algorithms for the snow depth estimation, and it's mainly using the multi-frequency, all-frequency passive. It's from 10 gigahertz to 89 gigahertz, and then we're using the new microwave snow emission model and also the AI technique to speed up the calculation. And it shows the bottom shows two results from the validation, and with and without the green size consideration. Next. So another one is over the mountain. It's basically what we found is our previous algorithm doesn't work well in the mountain area. It's a passive algorithm. So right now it's using the Sentinel, and it's basically modified. It's a cross-polarization algorithm. And so it's also using the enhanced resolution for passive from at a few kilometers. And we're also using the fraction of snow cover, so that using AI technique to training. So the bottom figure, it's showing comparing with ERA5, and you can see they have too many snow. And the bottom is actually the MERA2 is another reanalysis data, and also our microwave tradition product. And in the middle, it's actually measurements and also our algorithm. So it shows significantly reduced those errors. Next. But once we estimate the snow water equivalent, but what we find a significant problem. It's basically for our purpose is to estimate how much water is actually generated. But over the Tibet Plateau, it's actually many places has a discontinuous snow cover. It's the seasonal condition is not very clear. And also after the snow melt, it also has a new snow come and rain on snow. So it's basically our our microwave technique is actually failed. So basically for this, we try to develop a synergy between the satellite observation and the snow melting model. Next. So this is our synergies. It's basically we have the satellite measurements, and also we have the snow therm. It's probably most of people doing snow, and it's knowing this is the best physical-based model. Then we're using also the high resolution, the precipitation data, and we're using that simulate the density depth etc. And we simulate the brightness temperature measurements. Then we actually controls the observation constraints with multi-frequency and the snow-covered fraction to put the different weights, then finally generate different snow products. Next. So this is actually, it shows the water balance of the snow. It's snow surface is showing the rainfall on the snow, and also the output is melting water plus snow sublimation. So those are the you can see that during the past 20 years, what that average distribution. The bottom is the on the top is sublimation, and at the bottom is rain on snow. Oh, it's opposite. So the next. So this is actually generated products over the 20 years, and the column is 20-year average. So for special distribution. And in the middle, it's actually those three parameters for at the pixel scale for the change trend. So basically you can see the whole Tibet Plateau, all those three, the snow fraction cover, maximum snow water equivalent, and the melting water, they are all decrease. And another thing we can see is the maximum snow water equivalent only presented two-thirds of the snow melting water. Next. So this is analysis to distribute those at three different scales, and this is basically on the different climate zone. In the Tibet is westerly and the monsoon, and also the transition zone. And on the top is actually the average, the snow melt water distribution. So, and the bottom, the curve is showing the change trend. So you can see that basically the most of snow contributed to the westerly and the monsoon region, and the changes in the two drainage basin, it's more significantly. It's very large. And the next. So this is the last view graph, and it shows the snow water, melt water distribution to the runoff index, or how does that impact the water resource. And the runoff index is P minus E, or precipitation minus evapotranspiration. So you can see overall the Tibet Plateau is actually snow will become less and less, so become less contributing, and also over the different climate zone and the basin scale, how does that change it? This is actually my report. So this is we did the algorithm development. It's based on the characteristics of the over the Tibet Plateau, what is special conditions, and developed those algorithms. And then we also produced 3 kilometer, 20 years, 3 snow element data set. So those are support snow research and application. Thank you.
Okay, thank you for Professor Xu, and I would like to move to the next. But yeah, next talk is from Andreas Ders at DRR Germany, and his talk is about remote sensing based global snow and ice data products. Yes, please. Because yeah. A video system?
Yes, hello, and today I want to give you a short introduction and summary of the remote sensing-based global snow and ice data products that we have at DLR. And this is a presentation put together by myself and my colleague Celia Baumhoer, also at DLR. We have already since more than 10 years now started with the first cryosphere-based snow cover product that we have at DLR, which is the global snowpack. This one we started developing and also providing since we realized that although there are several global snow cover products available these days, like the Modis daily snow cover product and also from ESA and Copernicus, there are a few. Usually their problem is that there is cloud gaps and polar darkness gaps that are problematic when you want to do calculations like snow cover duration and the changes of snow cover duration over time. And if you want to compare different seasons with each other, it makes it very hard if you have data gaps in this. So we decided to put together a processing scheme where all these data gaps are being interpolated. The processor is based on Modis data in the initial phase, and now since a few years we are also offering a combination of Terra, Aqua Modis, and NPP VIRS. And we are processing almost 120 Modis tiles globally. We are not processing Antarctica, but all the other regions in the globe where we find snow cover. And this product is available since the year 2000 now on a daily basis with a spatial resolution of 370 meter, completely gap-free. And it's, of course, very useful to derive products and information such as the snow cover duration, or here on the left, as it's seen, the mean snow cover duration that we have over the whole time series. But then based on this, we can also have standard deviation, basically, of the snow cover durations of each particular year that we have to kind of get an understanding how stable the snow cover is in a particular region in the world. And then we can also derive other products like here the early and late season or beginning and onset and offset of snow cover. Basically, using this daily data, you can produce any kind of information you want. You could also, of course, derive monthly durations, even weekly durations, and see how this all plays out over time. And the idea here is, of course, that this product is being made publicly available through our EOC Geo service at DLR, so that any interested researcher and scientist can download this for their region of interest and use it to calculate potential trends or developments that they have in their region of interest. Here, this is just one example of the things that you can do. So we derived the snow cover duration trend basically for March, April, May. So you can say for spring season on a global scale, where you can then identify regions where you have declining snow, but also regions where you have basically increasing snow. And this is just one example. Of course, using this data set, you can derive this kind of information for any particular region or month or season or whatever you like. The second data set that we are producing at DLR is ice lines. And ice lines is a shelf ice front position data set that is being processed for whole Antarctica, and it is based on a artificial intelligence, a deep learning approach, a UNet architecture that is being developed by my colleague Celia Baumhoer. And what goes in is Sentinel-1 data. Basically, all the Sentinel-1 observations that you can have over the shelf ice front areas in Antarctica went into this processing and to detect the edges and then derive basically a monthly product. And this data set is now available since the year 2015 and is also being made available public on our EOC Geo service. So the interesting thing about, of course, the shelf ice front positions is also their dynamics, of course. If you see a huge decline or huge decrease of shelf ice area and basically a decrease of the shelf ice area, shelf ice edge, it can, of course, mean and lead to also mass balance changes and a loss of ice in Antarctica, which then, of course, translates to sea level rise. So using this kind of information about the position of the shelf ice front is important for also modeling the current mass balance of Antarctica, but also, of course, future developments, which is why this product can, of course, be very useful and is available for anybody who wants to download it. There has also been, in the context of this product, the Iceland product, there has been a publication or a release of a benchmark dataset. So if you are interested in training your own deep learning approach to detect the shelf ice front, or if you want to maybe modify a product or an algorithm that is out there, this benchmark dataset is also completely publicly available, and you can use it to train your own models. Okay, the third product that I want to briefly talk about is Polar Lakes, and Polar Lakes is a bi-weekly superglacial lake extent product that has been developed in the framework of an ESA project called Lakes for Antarctica, but also in the framework of a DLR project, Polar Monitor 2. And similar to the shelf ice front position, also the supraglacial lake and their extent are a good indicator for mass balance and mass balance changes of Antarctica. And of course, they can also increase certain other aspects like mass loss, melt, surface melt, and they are an important factor also if you want to model the overall mass balance of Antarctica. This is why this product has been derived and developed, also again based on a UNet approach, so a deep learning approach. In this case, though, it was important to use a combination of Sentinel-1 and Sentinel-2, so multispectral and radar data, because while supraglacial lakes are easily visible from multispectral data during cloud-free conditions, the problem is, of course, in the Antarctica that there is a lot of clouds and also a lot of darkness. So using only multispectral data from Sentinel-2, it is a big problem if you want to have bi-weekly information about the lake extent, which is necessary in this temporal resolution to derive any dynamics. And therefore, the processing chain has been developed to derive supraglacial lakes both from Sentinel-1, from the SAR data, and Sentinel-2. And in the end, both of these data sets are being combined to basically produce a very high quality output of supraglacial lake extents. This has been achieved now and is also available since 2015, basically, this product, and has been also published and is also available like all the other polar data sets that we have in cryosphere data sets in the EOC Geo service. So you can also from there access it and download it. And also the benchmark data set for this is planned to be released in the future. With this, I want to already conclude my short presentation. I have a few last remarks on the whole data sets and the whole cryosphere research that we do at DLR, because of course we see and we realize that making these products available to the scientific community is of really great importance. Also to us, we realized in the last years that having projects funded through ESA or Horizon or national ministries is a great way to develop something new. But the problem is once it has been developed and the project has successfully been concluded, these developments, they need to continue and they need to be continuously be available also to the scientific community. So we are in the lucky position that we can provide with the EOC Geo service, that we can provide access to these products. And we are trying to do that whenever it's possible and it's feasible. The problem is, of course, that when a project is concluded and finished, also the budget and the finances and the monetary aspects are gone, which means that there is no support to continuing to provide these products and these services. Usually when there is an operational service that has been developed, it's not a big problem for us. We can still try to maintain the processing and do automated kind of processing of the data sets. Once there is major updates necessary, however, it's a problem because we don't have the funding usually to really continue doing this. So far we can cope with that and we can overcome these limitations. But what I think would be important is also a strategy somehow to make sure that there is a way to continue providing cryosphere products, but of course in general all kinds of remote sensing based scientific products, because data formats change and sensors might change, and a sensor might not be available in the next decade or next year, and new sensors will come, and there need to be new developments that somehow need funding, and this is something that we are trying to figure out, and I hope we can find solutions for this in the future. Thank you very much, and if you have any questions, please feel free to contact me through this email.
Okay, thanks for the talk from DRR and Justice. So I will move to the next because the time is very, very tight. Okay, next from Marta Koch from UK. Oh, you changed the order. Oh, that is okay. We can. Number 4, okay. Okay, so we change it, it's okay. Yeah, it's fine. So Torsten, and we will move one ahead. The Torsten will focus on the AI latent learning and its limits. Yes, Torsten, it's
yes, thank you.
Use.
Yes, so I focus a little bit on the agentic side of it. So I come less from the geoscience, more from the AI engineering and governance. And the idea is that how much of the the agents, the agentic technology, the scaffolding, the harness around that, how it could be used actually to close the usage gap along the EO value chain, upstream and downstream. I think first it makes very sense to look into. Also, you have to do it. Or who's doing it? Are you doing it? Next one. Let's first look into what is actually this agent or the agentic structure, and this is pretty much luckily derived from the code leak of Anthropic, which happened a couple of weeks ago. Maybe you heard about that. And so a lot of code leaked about their harness. So it's not the model, the frontier model, but the structure around that. So on the left side, you see it's kind of said it's a training time model. How it's trained, and the middle part, which says number 2, is basically the runtime agentic structure. The yellow one is all the governance elements of such an agentic structure, and then the B and the C. The B is actually the runtime model, and C is when the agent is doing something or you prompt it, it always goes through the runtime control. Can I do that? Am I allowed to do that? Right? So it goes very fast, and you see when you use Claude Code or whatever, it always asks you. And actually, the model is prompting you. It is this runtime control which might prompt you, unless we really insist and you put it that it should not prompt you. And on the right side is basically the development of the harness of the agent, the framework, where, like, for example, Anthropic says 80% or whatever is already programmed by the system itself. So it becomes a little bit of a maybe an issue here. And the reason why I'm showing it is because when these frontier models further develop, how much of this agentic structure around it is absorbed by the model itself? So when there's a next release, and you heard this news about the Mythos, there's a lot of the controls around is absorbed by the training. So because it trains on behavior, so it can actually imitate some of the agentic structure outside. So next one shows that. It's basically in the middle, you have if you wish, the model, and it has all these kind of latent knowledge, cognitive and behavioral patterns. On the top left, this is what it's trained on usually, it's on the language, reasoning skills, etc., etc. And on the right side is the inference, what it can do. On the bottom, actually, you see this little bit thick, it says current thick scaffold. So the governance structure, basically, on the right side is the future thin scaffold. And this is just to indicate how much of it in the next releases the model is trained to absorb that. And the question is, how will it absorb everything? So basically, you have just a model and it does everything. I don't think so. So what is outside is probably the control and the enforcement, and of course the physical infrastructure, which is outside. But a lot of the cognition and the decision logic will be absorbed. So you don't need to put it into the memory MD in these files, do this or do that, and to remember this. It will just do it, right? So it will be very good in that. But there's a limit of this absorption. When I say absorption, is when it's trained for those things. Next one. So the next one is basically now a little bit of mapping what happens in EO. What can happen, I think, what's happening already in EO. So you have on the right side the frontier model, which is the brain in the let's say in an EO ecosystem, and on the left side you have I think what is very strongly pushed now is the geospatial foundation models, right? Because there's multi-task capable, and these geofoundational foundation models, what I call EOFMs, they absorb stuff, right? So it's like the frontier models, the LLMs. On the EOFM side, they absorb some capabilities. So all the traditional, let's say, task-specific activities, the EOFM will take over, right? So you can do multiple tasks with one of these foundation models. So you have this reuser representation. And of course, there are errors, there are mistakes, but I think that will improve. I think what is less absorbed is, of course, all these physics-informed tools, right? The PIN, the PINO, etc. I think parts of it will be also absorbed by training, right? But I don't think so, because you need basically an imposed physics-informed truth in that. So when the error function is for the LLM is this really a cat? Is it then it's for the PIN and so forth? Is it really the physics, the physical truth, right? So, and I think this might stay outside the model. So there's the good news. There's something which uses it. It will still be used, or the EOFM or the frontier model. It depends. They're also converging. Will of course use that tool. We will use the PIM to do the job. So I think what's happening is that when you look at the entire process, the EO process, so the upstream, so the image, the satellite data, even the mission planning of the will be basically automated by the agents, and also downstream. And downstream, the goal is, of course, to close the usage gap. So the next slide. So I'm almost done. So here I did say, when I come to Geneva, what are you looking at? So what I actually have myself on this, and we spoke a little bit, I have a complete open Claw system locally running on this laptop here. And it has a couple of agents. It uses a Quen model, a Gamma model, and then there's a super Gamma model, which is absolute unconstrained. And then of course, it has a Codex and Claude Code, this big one. And they're all linked together, and even they allow it, Anthropic and OpenAI to run as quasi agents in the Open Claw, which is open source. Okay, it kind of belongs not to OpenAI, but it's kind of open source structure running locally on this laptop, and that's easy. So I use a Clay model as an open source geofoundation. So can you get me some image data, etc., etc. And then I asked, next slide, I asked basically Real, that's her name. Sorry, it's not to anthropomorphize AI. What shall I do when I talk about this? And then the first bullet was quite interesting. You combine or you compare the urban heat islands in Geneva with a wealth structure, meaning the retail prices of real estate. And then I set the whole next slide. I set the whole structure. So I used a combination, and this is where the system learns of the clay model. I use an NVIDIA model. I use some kind of Pinot styled interpretation, and then and this is all orchestrated basically by the agents. Yeah, you see basically on the left side, the red is these heat spots, and the right is a little bit cool. And then I downloaded the late from 2024. The price index or the rent index of the real estate in Geneva, and I tried to map. And actually, the assumption was from the agent whether, when you are living in a high-priced real estate area in Geneva, it's cooler, right? You would say so, but it's actually the opposite, because traditionally you want to be closer to the lake. It's quite old. It's all it's all full of old buildings, etc. So it's pretty hot there compared to the cheaper areas. And the cheaper areas, and I mean Geneva, nothing is cheap, is more the orange here or the red area. Anyway, and then the next slide, I'm almost done, is basically, then I asked Paul is another agent, is he happy with this conclusion? And of course he's quite careful, and the conclusion is then what he said is: a higher prices appear more strongly associated with central lakefront urban value than with cooling advantage alone. So this is just so the last slide, I think, then we are already done. The next one. Yeah, this basically to show that, and this is done in an evening. This is done in an evening to get all the data, to call on the tools. And actually for this agent scaffold, it doesn't care. It just searches the tools. And of course it has some knowledge already. I use this one, and I have some local tools. It knows that, so that some of the technologies we're using become tools in the background. In the future, we will not even recognize that we have these tools. And I hope no one is from S3 here. That is kind of a big challenge for those application companies, or like SAP, etc., that their tools are all going into the background. And I think that was a quite good demonstration. Thank you.
Okay, thank you, Torstein. So we'll move next for Martin Koch from the UK. The talk is about data running.
Second, yeah, thank you so much for inviting me to give a talk as part of this event, and it's great to collaborate again with the Geo Cold Regions Initiative after our joint UNECE Regional Forum Sustainable Development event last month on digitalization and climate extreme. So to check that out on the website if you're interested. Yeah, thank you so much. So I'll be talking about data readiness for climate mitigation extreme environments. And yes, I'm from Imperial College London in the UK, a UNESCO Science Report Coordinating Lead Author and UNFCCC Technology Executive Committee Activity Groups member. Please move on to the next slide. Thanks. Yeah, so we're seeing a few key trends in terms of data readiness and availability, specifically satellite data. So here's some research from Precedence Research, a graph showing up trajectory and projections for up to 2034. Yeah, hopefully the mic will work. Yeah, so we can see certainly the global satellite data services market is increasing and is predicted to increase in the next 10 years. And it's definitely a very clear positive upward trajectory there. So the availability of data and the data services market really increasing there in terms of, and that has huge implications for data availability and readiness. Next slide, please. The second trend we're seeing in terms of data readiness as well for climate data and all data, satellite data, is the resolution and the accuracy of the data, and that has implications for, obviously, as you can see, there's publication there, privacy as well, and privacy for kind of individual household level. So yes, this is the second key trend. You can see this is research from Dennis and Di Pietro, published 2025. live in IEEE Access that shows, again, a very positive correlation, positive upward trajectory in terms of the resolution and accuracy of the satellite data that we're getting as well, and the increasing number of satellites available as well. Next slide, please. Okay, I hope, yeah. I've been asked today to speak specifically about extreme environments and climate extremes. I'm going to speak specifically about cold extremes. And so key case studies that we have that are very, very relevant in terms of data availability and data accuracy, and the two key trends that I previously mentioned. We've got the Arctic permafrost data. We've got Greenland ice sheet data. More specifically within the Arctic, we've got Antarctic ice shelves, and then high mountains, or sometimes called the third pole. Himalayas and the Andes is a key example of that. So in terms of Arctic permafrost, what kind of data is becoming more ready and increasing in data readiness? We're seeing methane and infrastructure risk data, satellite and AI monitoring, and geo AI, so AI being integrated into geospatial data, and then that improves data prediction of emissions. In terms of the Greenland ice sheet, AI and satellites combined are getting better at detecting accelerating ice loss, and GeoEye is improving sea level rise estimates. This is reducing uncertainty, specifically in terms of climate risk. In terms of Antarctic ice shelves, we're seeing better data and a greater data readiness in terms of extreme weather and data gaps being addressed, autonomous sensing systems being used, and real-time monitoring for early warning systems also improving. In terms of high mountains, glacier melt is threatening water security in these areas. So AI is being used, and geo AI integrations are being used for downscaling hazard mapping, and this is in creating better forecasts for climate resilience planning. So key enablers of data readiness and data accuracy improvements we're seeing are AI, geo AI, and digital innovation more broadly. So this is in terms of the physical technology infrastructures. Aside from satellites, we're seeing this in sensors and drones, and they're being used in combination with satellite data. Data platforms which are fair and secure, that's increasing in terms of data readiness, and in terms of geo AI and artificial intelligence, this usually falls under two categories: machine learning and digital twins, which are data readiness is really improving there, and automation of sort of data analysis. This has implications for insights, and that's in terms of policy as well as science and science policy interface, and is improving in terms of climate, risk assessment, planning, and also obviously climate policy and finance as well. So the key message I want to emphasize here is better data leads to better decisions and lowering of climate risk. That's the idea anyway. And to overcome the physical climate extreme challenges are in these climate extreme case studies that I'm highlighting here. We've got the Arctic, Antarctic, and high mountains, or the third pole. We must turn to digital layout in order to overcome the physical challenges of collecting data in these climate extreme, often remote regions where scientists sometimes can't access. So I want to highlight some research from Imperial College London, my institution, in this space, in data readiness improvement. So that we've got some research from the Grantham on climate risk modelling for more resilient communities. The Department of Earth Science and Engineering, of course, is doing some research on this, on Antarctic ice sheets. There's some international collaboration and collaboration with work such as the Arctic Passion Project on Arctic observing systems data interoperability. Got there eventually. And obviously the Centre for Environmental Policy. There's my own research and the iAdapt Climate Adaptation Project collaboration. And then some third and then some additional cross-disciplinary impact, which is happening across Imperial and has happened in the past in terms of high mountain altitude and third pole areas as well. Next slide, please. Okay, so in terms of implications for strategic priorities across science and policy resulting from greater data readiness, we are seeing an increase in open polar data systems in line with FAIR principles. Also, more recently, greater investment in low carbon AI infrastructure. So this is kind of energy efficient computing for climate science. Perfect, thank you. And a greater integration of indigenous knowledge and international collaboration across the climate extreme. So linking Arctic, Antarctic and mountain observing networks and science and data as well. However, we do still have remaining data challenges, persistent gaps in data, sparse data in some polar and mountain regions, interoperability challenges, inconsistent data sets, equity and governance challenges. Of course, indigenous knowledge is often underrepresented, and also community integration isn't as widespread as it should be. And sometimes we even have data overload as well. Too much geospatial data means that we need to sort and identify what's relevant and what isn't. And that's quite often where AI and machine learning comes in order to facilitate that process. Emerging scientific developments in the recent last 3 years in this space have, as I said, artificial intelligence, and other speakers have also raised this as well, and in order to improve forecasting and the sorting of large amounts of data, sometimes too much data. Digital twins for polar system. This is real-time models of ice sheets and tipping points in the polar region, and autonomous climate monitoring, so combining physical tech such as drones and solar wind powered networks in order to expand the coverage of data collection. GeoAI for disaster preparedness is a key thing that's been developing in the recent years. Polar wildfire, flood and sea ice risk assessments have improved in this way, and also smart analytics and decision support. More recently, again, machine learning and artificial intelligence has been a key tool for this. At the bottom there, I've shared some of my own publications on this topic. Please feel free to have a look. Yes, thank you so much.
Thank
Next
you
slide.
for Marta for the presentation.
Yeah, thank you.
I will use several slides to the last presentation. It's very quickly about the geocclusion. discuss.
Yes, thank you. I'm smack bang in the middle of the the panel, so I'm going to have to keep turning my head. Thank you so much. Yes, I'm happy to moderate the panel today. So my first question is for Dr. Frosten Jelinek. Yes. So thank you so much for your presentation and for sharing your work. So why does ensuring we have high quality cryosphere datasets still make sense in the AI era? And what kind of data most suited to AI training? What are the key challenges we need to navigate in terms of privacy and security, for example?
Thank you for the question. And obviously also I have to turn it on again. Yes. You know, if you in the presentation you say if you rely on the agents, you know, helping, augmenting the work, let's say the application, it's really up to the data, right? So it tries to find the data, so the access of the data becomes the problem. The whole handling, the interoperability, actually you said it yourself, and if this is not there, is not accessible, the agent can't do anything. So if we push for automation, and I think the automation here is actually a positive thing because it brings this the products closer to those who have to implement certain, you know, SDG activities, etc. So the data is obviously key, and what I saw is that then the agent actually will synthesize data and use the synthesized data to run a Pinot, and of course, but then it warns you it's a little bit cheating. So I think that's very important. The second question, maybe to the privacy issue, this just remembers a meeting we had, I think last year it was in Beijing with the International Red Cross, and Red Cross does crisis. Not prevention, it would be nice, but it helps in crisis situation, and usually it's about a war situation. And the usage of data and AI can be very problematic, of course, where it can be misused, etc. And I think we should be aware of that because we have a lot of knowledge how, you know, how to make disaster recovery, etc. But those can also be misused, right? So I think that's the biggest challenge. And I think collaborating with different institutions like the Red Cross, I think we can learn a lot. The frontier labs, or also institutes and Earth observation, and how to become conscious of those challenges. Thank you.
Thank you so much, Dr. Fulston. And then my next question is for Professor Zhongsheng Shi. Hopefully I pronounced that correctly. Please correct me if I got that incorrect. So how do we ensure we have high quality data sets available for use in cryosphere science and operations, especially in terms of global Earth science and environmental data?
Yeah, I think that probably all those high quality data is more close to whatever we are currently understanding for truth. So the conclusion or the policy and every adaptation or method, they all depend on how those data, the quality. So the poor data quality will generate a wrong decision, and also it will provide for the good model validation for our Earth's future prediction, and also the hazard of all of those applications. Thank you.
Thank you very much. My next question is to Professor Yuba He. Yeah, on snow and ice data sets. Yes.
Okay, so thanks for that.
Yes.
So I would like to answer the international collaboration under the GEO umbrella. So that is most important for the cold region operation. So okay, yeah. So this just like Jianqin Shi mentioned that the high quality data is represented that, you know, we can see the in situ measurement more. So this is the most important because we reflected the Earth systems and Earth science. But we know that with WMO and also the UNESCO and even the GEO, they have a different community based on the operation of the different countries. So in different countries, the division is different. So we would like to see how the international collaboration under the GEO umbrella, that is important. We would like to see explore, for example, WMO, they have a hydrology and also cryosphere. And even we know that we have ISIMO, and we have the Mountain Initiative, and we have the UNESCO Science Decade of the cryosphere. So this is very important to return back to the Earth observation site, include the in-situ measurement, or even the space part. But GEO is much more about the global link and average use the satellite based on that. So we face on the WMO, we face on that one. We would like to have some coordinator. Is quite important for that. So this is what I would like to push. Yeah.
Yeah, fantastic. Thank you. And Professor Ali Nadir Aslan, also the same question to you. Snow and ice data sets are critical contributors to cryospheric science, especially in climate extremes. So why is international collaboration under the GEO umbrella critical for this?
I mean, the one that the fifth one you're talking, or
number 3.
Okay, so same question.
Number 3, yeah,
okay.
same question, yeah.
Yeah. So basically, I have also some words of this the second question, the high quality data, because that is somehow this related with this also the third question. So because this we should understand that what is the high quality data set actually. So when I ask this the AI ChatGPT, that you can say that what is high quality data. So most of them that they are talking about this accuracy, spatial resolution, I mean high resolution, and then also the interoperability and so on. But I think in practice, when we talk about this high quality data set, when we are user, I think we need also that considering on this the next steps for this AI word that we are driving. So actually usefulness and usability becomes as a kind of the criteria, in my opinion, in the high quality data set that when we consider. Why I'm telling this usability and usefulness, because we have we are not actually, of course, there are some kind of, we have this still struggling of the data that we are missing, some kind of the areas, the sparse area, because we are talking about the cryosphere, because very extreme environment. So we don't have the data everywhere, but still we have a lot of data that we are, and then of course this is the institute data we are talking about, but then when we talk about the space data, we have already available with big available data. So this is not the question anymore, but then how this data actually used, and then how this data actually is useful for the end users. And now we have to make this the outcome and user-centric. So that's how I call as a high-quality data, because you can have a lot of data somewhere, because we have lots of data portals that available. So that, but I don't know how many of them that when you look at the data, then how many of them actually are not useful and not used. They are there. That's it. So so this is not high-quality data. In my dictionary, I mean, that's what I want to put this the things that. So then the question that this actually the snow and ice data are critical contributors cryospheric science, but of course that I don't know that this is the all kind of this. I mean. This is without data we can't have this we cannot do anything, and then especially in the extreme settings, climate extreme settings, and then we are talking about this now, the climate this change, and especially when we talk about the cryospheric things. So this is again comes back to my this usefulness and usability understanding data. For instance, how we can estimate the flooding, for instance, how can we estimate this natural hazards? I mean, these are the extreme events that are coming up. So that's why we need to understand that when we look at the data, not only collecting the data, but how this data will be how will be end outcome, and how will be how will be the use by this in event or by this for the stakeholder. So I think that's why it's very important, this snow and ice data sets that, I mean, very critical, of course, this cryosphere science. But if we are going that direction, that understanding that their usefulness and usability in monitoring this extreme settings. So, and then international collaboration, of course, it's very important. So because simply we cannot go, for instance, China to make a measurements. China cannot come to make I mean, so that's why I think data sharing and this geo is has an important role on this. I mean, I'm just giving on China because this is the now, and now for instance, we don't have a data in Russia. I mean, so now, maybe this will be a political statement, but I don't want to do that. But just to give you an idea that that without collaboration, we cannot access the data. So if we cannot access data, we cannot estimate things. So maybe with this,
Yeah, I have a follow-up to that. So why is it relevant for international collaboration and data sharing extremely important in climate extreme settings, and why does that have a global implication?
Yeah. Yeah, of course. I mean, as we now this Earth system, Earth science that when we talk that everything is connected to each other because it's cryospheric and atmospheric and there's all this ocean and they're all this like kind of they collaborated each other. So it's not like things are not happening in the regional or continental level. It happens globally. So that's why we need to understand. Of course, there are some kind of we are seeing this the effects like this local and regional impact, but actually these events as a global event. So that's why I think it's very important the collaboration.
So I have a question for you about, for example, you know how now we are facing a new AI time that is the game changer. So how this AI can help, for example, us, we cannot say that it's data sharing, but we can harvest the data from the AI system. That is much easier than before.
Yeah.
So this is a very, very promising way for the data sharing. Even you get the data from, for example, for the Russia area. I think they have lots of data already published online, but it's very difficult to collect them. So this is a way that for the AI can help. This is one way. Another is, for example, like AI can help to reconstruction of the data sets. So this is another way.
Yeah.
It's a generative AI system, deep learning systems. So this is what's your opinion about that?
Yeah. Actually, these are the two points are very good because I think they are kind of linking that what I said that, for instance, now we are talking about this analyst ready data set that now also the high quality analyst ready data set. But actually, maybe Torsten also can answer that. High analyst ready data set actually meaning that training data set for AI, the machine learning, right? That's what we are talking about because that's why that we are aware of that. If this training data is not accurate or is not useful, I mean, it again coming on usability and usefulness, because whatever because the machine learning doesn't do it themselves. We train them. So what we train them, it comes out. So again, answering your question that how these machine learning techniques can be useful, they can be only useful if we have the high quality data set in terms of the accurate and usefulness and usability parts included in this concept. I mean, because that data set we are going to use for training, then I think the AI is fantastic tool to be used. And another thing, actually, one project proposal that we've been writing that we have been considered this for me, for instance, that this interoperability is very important, and then there's all these data collection methods and guidelines, and are very different. We have all these different continents, different country has a different methods and different tools. So what AI can do, as a human, we cannot do it because there are plenty of this. If you call it the snow measurement, there are plenty of the tools that they measure these different parameters, and so. But machine learning, AI, maybe can do this, and we can put all this guideline input, and then maybe harmonizing, and then it can be done. This, for instance, we have prepared a data set in certain tool, certain sensor, because there are lots of sensors and satellite, and then maybe AI can harmonize this data set in terms of to be useful to the problem that we are solving. Maybe the machine learning can be that very helpful on that.
I've got a few minutes left. Is it okay to?
Yeah.
Next question to Dr. Forsten Jelinek regarding the importance of open science and good data and AI governance in terms of this. So for AI models being integrated for advancing cryospheric data sets and services.
If you allow, I would just maybe to complement, also to agree. I think it really depends on which stage you are, whether you train a model. So if you take the geospatial foundation models, of course there are mistakes still, and there's evaluation practices, and they are getting better and better. And the good thing is that they are multitask basically, so you can use them, reuse them. And so you need just a fewer samples, maybe 100 samples, whatever, to put it into the geospatial model. And then, on the local, like a city level or whatever, can use that. So it's a very practical approach. But of course, you still need to learn those geospatial models, and they absorb a lot in the future. And you see the large language models, how strong they get. We speak less about hallucination. What they actually do, these LLMs, they're not hallucinating. They make shortcuts. Right? If they can't solve a problem because they have they have a skill, and it's kind of hard defined, use this tool, and then suddenly they forget that, and that happens, and then they start programming. Then they make some script and do a brute force, and that's wrong. And with the data, I realized that if the data kind of not fitting, that's a good story. They make it that they fit. Right, and then they test it and said fits, I go to continue, and that's but there's a limit to that, of course, right? So if there's no data, they can't fit anything. Of course, there's maybe synthesize something. So I think it gets more powerful in this respect. So I think I didn't answer the question yet, but
You covered it. We believe we're on time. So would you like to move on to the closing or the final question?
I think we can close here, and I will. So JC would like to say something about that last question about the GeoCree activities later for the next step. That would be much valuable, and I will make a close. Yeah. Yes, please.
So for the what I'm thinking is for GeoCree, for this activity, probably we need to identify what is currently most reliable data. And this must be published. It's like a ESSD or scientific data, but it's published. And typically, we have a few global data sets for snow cover, for the sea ice, and etc. But the typically global type of product always has a problem. At a different region, they have the different problem, so that we probably added a regional also. So we have the global for the baseline, then we have start adding the regional products. And the third one is we try to reach out for different the whole community on the cryosphere, and provide the validation. We start to validate and gradually improve our understanding to see which data set will be the best use.
Okay, thank you.
One comment about this.
Please, yes.
Because to your slide that I see that portals. When I see portals now, I'm really now terrified because because I did a work for the European Environment Agency about this snow and ice. That because we are looking for the sparse areas that collecting the existing data, how many years. And then we went through like, I don't know how many, one of my colleagues, that there's a 50 or 60 portals that we have to go through and look at this, what data is there, and then who is providing and what is that. And so maybe something not portal, but we maybe some guidelines, some kind of these things. But I think portal is we have to be careful on this, not creating another level of complexity of this.
Yes, right. Okay. Yeah. Okay. Thank you for the speakers and also the panel panel expose, and I would like to really quickly to conclude this. So actually, we are looking forward for the next step of the GeoQuery, and also I think we could do something better than before with the artificial intelligence. So that is why we need the high quality data. Otherwise, if the AI training based on the bad data, they were garbage in and garbage out. This is the regime of the AI systems. So thank you all. Let's close it. Thank you. Yeah.